Hello students, I hope that you are good, well and fine. In today's session, we will be seeing addition of two vectors. So how we are going to add vectors? So let's see. If you are having vector AB, simply means the displacement from a point A to the point B. Now consider a situation where a girl moves from A to B and then B to C. Okay, then the net displacement made by the girl from the point A to the point C is given by vector AC. Clear? As you can follow this figure. So A to B, this means AB vector, and B to C means BC vector, and then net displacement will be A to C, this means AC vector. So AC vector will be what? The sum of AB and BC vectors. Okay, so this is known as the triangle law of vector addition. Okay, in general, if we have two vectors, small a and small b, as you can see, small a and small b vector, then to add them, they are positioned so that the initial point of one coincides with the terminal point of the other. As you can refer this figure, it represents that if this is your small a vector and this is your small b vector, then as you can see, this terminal point of a vector is same as the initial point of b vector. In order to find the sum of them, or in order to add them, okay, then you will get your AC vector as vector a plus vector b. Okay, clear? Now for a minus b, as you can see this diagram. Okay, so this BC represent what? BC prime. So this vertex is what? C prime. As you can see, this BC prime vector represent what? The same magnitude but the opposite direction of BC, represented by minus or the negative of vector B. So that's why minus B vector. Then this will be what? Sum of A and minus B. This means vector A minus vector B. So this represent your vector A minus vector B. Okay, so we have already seen that in this second we have shifted B vector without changing its magnitude and direction, so that its initial point coincides with the terminal point of A. Then the vector A and B, if you add them, this will be represented by the third side AC of the triangle ABC, gives us the sum, or you can say resultant of the vector A and B. That is, in triangle ABC we have vector AB plus vector BC is equals to AC, as you can follow this. Now again, since AC is negative of CA, we have already seen that negative vector. Okay, so our equation can be represented in this way, that AB plus BC is equals to minus CA. Okay, minus CA, and this CA can be taken to the left hand side. You will get AB plus BC plus CA vector is equals to 0. 0 vector means AA, the same initial point. If you have initial and terminal point same, this means your vector will be its 0 vector. So this equals to 0 vector. This means that when the sides of a triangle are taken in order, it leads to 0 resultant, as the initial and the terminal points get coincided. Okay, now the third figure, as we just already saw, that we constructed C prime, okay, which represent BC prime vector. So its magnitude is the same as BC vector, but the direction is opposite. So that's why BC prime vector is equals to minus of vector BC. Okay, if you use the triangle law here, you will get what? AC prime vector will be the sum of AB vector plus BC prime vector. This will be AB vector plus minus of BC vector. This means A vector A minus vector B. Your AC prime vector will be vector A minus vector B. Okay, clear? Okay, now consider a boat in a river going from a bank of the river to the other in a direction perpendicular to the flow of the river. Okay, then it is acted upon by two velocities vectors. One is the velocity imparted to the boat by its engine, and other one is the velocity of the flow of river water. Okay, under the simultaneous influence of these two velocities, the boat in actual starts traveling with a different velocity. To have a precise idea about the effective speed and direction of the boat, we have the following law of vector addition. Okay, so if we have two vectors, vector A and vector B, represented by the two adjacent sides of a parallelogram in a magnitude and direction, as you can refer this figure, then their sum vector A plus vector B is represented in magnitude and direction by the diagonal of the parallelogram through their common point. This is known as parallelogram law of vector addition. So as you can see, this is your initial point for vector A, for vector B. Okay, so parallel to this vector and with of having same magnitude, you draw AC vector. Okay, parallel to this small a vector, you draw BC vector having same magnitude. Okay, as you can see. So now just join your this two opposite vertices. You will get your diagonal of a parallelogram. Then this diagonal represent your what? Vector A plus vector B. This is what already written over here. Okay, now note that from the above figure, using the triangle law, one may also note that OA plus OC vector, both vectors, is equals to OC vector. Sorry, OA plus AC is equals to OC. As you can see, OA plus OA plus AC is equals to OC, as you can see, or OB plus BC, OB plus BC, or in other words, AC is just same as what? OB. So that's why OA plus OB is equals to OC, since AC and OB both are same. Okay, so which is parallel law. Thus we may say that the two laws of vector addition are equivalent to each other. Clear? Now properties of vector addition. So commutative property holds that if you add A first and B later on, this will give you the same result as if you add B first and A later on. Okay, now proof. If you try to see the proof, you have a parallelogram ABCD. You can refer this diagram. AB vector is represented by small a vector, BC vector represented by small b vector. Then using the triangle law, from triangle ABC, we have AC vector is equals to vector A plus vector B. Since the opposite sides of a parallelogram are equal and parallel, refer this diagram, we have AD vector is equals to BC vector is equals to small b vector, and DC vector is equals to AB vector is equals to small a vector. Again, using triangle law, you will have that in this ADC triangle, in this you will have AC vector is sum of AD vector and DC vector, which is B and A. So hence AB plus A plus B is equals to B plus A vector. Okay, I hope it is clear. Now second property says associativity. It holds associativity also. Okay, clear? So now PQ, QR and RS, PQ, QR and RS, as you can see respectively, as shown in this first part of 10.11 diagram, and second part also, PQ, RS. Okay, now what is happening, as you can see, that A plus B, this can be represented by sum of PQ and QR, yes, which is equals to PR. PR what? Vector PR is sum of two vectors, which is vector A plus vector B. Okay, now the same can be done for this B and C. For this triangle QRS shaded in blue, you will have what? This QS vector will be what? QR plus RS vector. Yes, as you can see, B plus C. Okay, now what is this PS vector? PS vector is, if you try to see in this white triangle, you will have PR plus RS Yes, and what about this? This will be PQ plus QS. Okay, PQ plus QS. Now combine all the information you are given. You will have vector A plus vector B first plus vector C is same as vector A plus combine or add first vector B plus vector C. Okay, you will have this result. This means associativity also holds. So the associativity property of vector addition enables us to write the sum of three vectors A, B, C as A plus B plus C without using any vectors. Any brackets. Okay. Now note that any vector A we have A plus 0 vector is equals to 0 vector plus A always gives you A. Okay, as the 0 vector is called the additive identity for the vector addition. Okay, I hope now it is clear that how we are going to use our vector addition information and what are the laws, what are the properties. Okay, now multiplication of a vector by a scalar. So let small a vector small a be a given vector and lambda be a scalar. Then the product of the vector by the scalar denoted by lambda times vector A is called the multiplication of a vector A by the scalar lambda. Note that this lambda A vector is also a vector. Okay, this result will also be a vector and collinear. It must be collinear to this vector. This means parallel to this. Okay, vector A. The vector lambda A has the direction same or opposite. It depends on what the value of lambda we are taking. If you take -1, lambda is your -1, then the direction will be opposite. If you take lambda is equals to 1, then the direction will be the same. Okay. Also the magnitude of vector lambda is absolute value of lambda times the magnitude of A. Okay. So if you have to find the magnitude of this, this is written in this form also, mathematical form. This is magnitude of scalar multiple, okay, of vector A. This will be same as absolute value of lambda product with absolute value of or the magnitude of vector A. Okay. Okay. Now geometric visualization of multiplication of a vector by a scalar is given here. So A is this. If you multiply with half, you will have this length as half. The direction remains the same, but the length, okay, the length of this vector is now reduced to half. This vector. Now if you multiply with 2, now the direction remains the same, where the length becomes now the twice to the original. What if you multiply minus half? This means the magnitude gets now is reduced to half and the direction is now opposite because of this minus sign. The same will happen for this. The direction is now reversed, the opposite. The magnitude is now twice the original magnitude. Okay. So we have used what? Clear? Okay. When lambda is equals to -1, then lambda is equals to -a, which is a vector having magnitude equal to the magnitude of A, but the direction opposite to that of the direction of A. Okay. The -a we will be calling it as negative of a vector A, and we will be calling it as a additive inverse. Okay, so which means vector A plus minus vector A will give you 0 vector, or minus vector A plus vector A will give you 0 vector. Using commutative law we can write this. Okay, so this -a will be your additive inverse. Now if lambda is equals to 1 by modulus A, then you will have absolute value of lambda vector A is equals to absolute value of lambda multiply with magnitude of A. You will have 1 by lambda 1 by magnitude of A multiply with magnitude of A. This is equals to 1. So this represent what? Your unit vectors. What represent your unit vector? This, that lambda multiply with vector A represent your unit vector only if lambda is represented like this, or lambda value is this particular. In this particular case you will say that your lambda multiplied vector A will be your unit vector. Okay, in other words, that, and a unit vector, we all have already seen that unit vector is represented by a hat. So a hat is equals to 1 by magnitude of a multiply with vector a. So unit vector will be this. So if someone asks that this is your given vector, then find your unit vector. So simply what you have to do is take that given vector divided by the magnitude of the given vector. That's it. You will get your unit vector in result. Note that if any scalar k multiply with 0 vector, you will always get 0 vector. Okay. Now components of a vector. So let's talk about components of a vector. Suppose we are having 3 points a, b, c, as a as 1 0 0, b as 0 1 0, c as 0 0 1 on the x-axis, y-axis and z-axis in 3D space. Then position vectors for a, b and c points will be OA vector, OB vector and OC vector, having magnitude same, which is 1. This means OA, OB and OC vectors are unit vectors. Okay, unit vectors. So vectors OA, OB and OC having magnitude 1 means unit vectors. Okay, along what axis? Along OX axis, OY and OZ respectively. Okay, and these unit vectors represented by I, j, k hat, I hat, j hat, k hat respectively. Clear? So OA vector, we are representing it as by I hat, OB as j hat and OC at k hat. Okay, magnitude of their I hat, j hat and k hat will be 1. So that's why we are calling it them as unit vector. As you can see, I vector will be along with x-axis, j vector along with y-axis, k vector along with z-axis. Okay, I hat, j hat, k hat. Clear? Having magnitude 1. That's why we are naming them as unit vectors. Now consider the position vector OP of a point P, as you can refer this above diagram. As in figure 10.14, also refer this. Let P1 be the foot of the perpendicular from P on the plane XOY. So plane XOY or XY plane, the P1 point represents the foot of perpendicular. Okay, this means that you are having your point P. If you draw a perpendicular on XY plane, okay, on XY plane, the foot of the perpendicular will be P1 point. Okay, we see that the P1P is parallel to z-axis here, as I, j, k hat are the unit vectors along the x, y, z axis respectively, and by the definition of coordinates of point P, we have P1P vector, initial point is P1, final point is P. So this means this vector P1 to P, this means direction is upward, is same as OR vector, yes, which is same as Z times K hat. Yes, Z times K hat. Okay. Similarly, QP1 vector is equals to OS. So Q, where is your Q? So Q is this. So QP1, this vector is same as OS vector. This means Y times J hat, and OQ will be same as P1S. This means you will have X times I hat. Okay, I hope it is clear now. Now OP1 vector is same as OQ plus OP1. As you can see, OP1 will be in this triangle OP1. You will have OQ QP1. This means XI hat plus YJ hat. Similarly, this means OP vector will be sum of OP1 vector plus P1P vector, which is xi hat plus yj hat, because OP1 is xi hat plus yj hat, plus P1P vector will be just jk hat. Hence, the position vector of P with reference to O is given by OP vector will be xi hat plus yj hat plus zk hat. Okay, so if you have a position vector of P with reference O, reference means initial point is origin and final point is P, given by this xi hat plus yj hat plus zk hat. Okay, clear? So any point with reference to origin, okay, or position vector can be represented in this form. Okay, this form of any vector is called its component form. So this form we are calling it as component form. So here x, y, z are the scalar components of R vector, and xi hat comma yj hat and zk hat are called the vector components. So scalar components are these x, y, z, whereas vector components are xi hat, yj hat, zk hat. Okay, sometimes x, y, z are also termed as rectangular components. Okay, now the length of any vector R xi plus yj plus zk, we will be applying what? Pythagoras theorem. You will get what? That OP1 length magnitude will be root of x square plus y square. OP1P will have what? In right angle triangle, in this OP1P you will have OP magnitude as root of x square plus y square plus z square. So this gives you magnitude of R. This means magnitude of xi hat plus yj hat plus zk hat is equals to root of x square plus y square plus z square. Clear? Okay. So this will be your magnitude of any vector of form xi plus yj hat plus zk hat. So if any vector, two vectors a and b, okay, in component form a1 I hat plus a2j hat plus a3k hat and b1 I hat plus b2j hat plus b3k hat respectively, then their sum will be a1 plus b1 I hat, a2 plus b2 j hat, a3 plus b3 k hat. The difference will be a1 minus b1 I hat, a2 minus b2 j hat, a3 minus b3 k hat. If they are equal, then a1 must be same as b1, a2 must be same as b2, a3 must be same as b3. Multiplication by a scalar will be what? Lambda times a1 lambda times a1 I hat plus lambda times a2 j hat plus lambda times a3 k hat will be your multiplication of vector A by a scalar. Okay, I hope it is clear now. Let's see that if you have two vectors a and b and k and m are some scalars, then k a vector plus m a vector will be same as k plus m multiply with a vector. K multiply with m a vector is same as k multiply m now then multiply with a vector. Now k multiply with sum of two vectors will be same as k multiply with first vector plus k multiply with second vector. You can distribute it. Okay, now some remarks. One may observe that whatever the value of lambda, the vector lambda is always collinear to the vector A. Yes, in fact two vectors A and B are collinear if and only if there exists a non-zero lambda such that B vector can be rewritten as lambda times of A vector. If the vectors A and B are given in the component form like this, then the two vectors are collinear if and only if that this B vector is lambda times A vector. Yes, this means compare things. You will have B1 is same as lambda times A1, B2 is same as lambda times A2, B3 will be same as lambda times A3. This gives you that A1 divided by B1 is this ratio, B2 divided by A2 this ratio and B3 divided by A3 this ratio, all ratios must be same, equal to some constant scalar. Okay. Now, if this component form, which is A is equals to A1 I hat plus A2 J hat plus A3 K hat, then A1, A2, A3 are called direction ratios of A. Clear? We have already seen direction ratios. Okay. Clear? Okay. Now what? Now this gives the second point. Now the third observation. In case if it is given that LMN are direction cosines, this is direction cosines. Okay. Direction ratios are different. Direction cosines are different. Okay. So this LMN are direction cosines of a vector. Then L I hat plus M J hat plus N K hat will be same as cos alpha I hat plus cos beta J hat plus cos gamma K hat is the unit vector in the direction of that vector. Okay. Where alpha, beta, gamma are the angles which the vector makes with x, y, z axis respectively. Clear? Okay. Now example. Let's see some example to understand more. So find the values of x, y, z so that the vectors A and B are both equal. So this means x must be same as 2, 2 must be same as y, and z must be same as 1. We have already seen. Okay. If A vector and B vector are these, first of all we have to show, or we have to conclude that is magnitude of both the vector equal or not. So let's see. So magnitude of vector A will be 1 square plus 2 square and then root. So it will be root 5. What about B? So 2 square plus 1 square then root. Yes, both the magnitude same. So true, it is true that both vector magnitude is same. Now, are the vectors equal? No. Why? Because the two vectors are not equal since their corresponding components are distinct. Two vectors are only equal when their corresponding components are same. This means, okay. So now next, find unit vector in the direction of this. So you have to find unit vector. You all know that how we are going to find the unit vector. First of all, we need to find the magnitude. So magnitude will be root of 2 square plus 3 square plus 1 square. This means root 40. Now divide your A vector by just root 14. You will get your unit vector and represented by A hat. A hat will be 2 divided by root 14 I hat plus 3 divided by root 14 J hat plus 1 divided by 14 K hat. Okay. Clear? Now you have to find a vector in the direction of this vector that has magnitude 7. So in order to find a vector in this direction, you have to, and that vector magnitude must be 7 units. So how you are going to find? Quite simple. First of all, find the unit vector of this. So in order to find the unit vector, you have to divide this vector by its magnitude. So you will have the magnitude will be what? Root of 1 square plus minus 2 square. So this will be root of 5, as you can see. 1 by root 5 I hat minus 2 divided by root 5 J hat will be your A hat. This means unit vector of A. Now, therefore the vector having magnitude equal to 7 and in the direction of A will be what? 7 times this. 7 times unit vector of A. You will get. Now if you try to find the unit vector, sorry, if you have to find the magnitude of this vector, you will get 7 and this direction is same. Okay. Clear? Okay. Now find the unit vector in the direction of the sum of vectors. So direction of the sum of vectors. So first you have to sum. So add corresponding components. You will have 4 I hat plus 3 J hat minus 2 K hat. So 4 I hat plus 3 J hat minus 2 K hat. The magnitude of this will be 4 square plus 3 square plus minus 2 whole square and root. This means this means 16 plus 9 plus 4. You will have root 29. Yes. Now what? Now magnitude for C will be this, C vector will be this. Now find the unit vector. This means C hat. This means divide C vector by its magnitude. You will have 4 by root 29 I hat plus 3 by root 29 j hat minus 2 by root 29 k hat. Clear? So you will get your unit vector. Okay. So this is it for now. Okay. So there is only one example remaining. So let me just quickly go through it. So write the direction ratios of this vector and hence calculate its direction cosines also. So direction ratios are the what? If you have a vector, what? So direction ratios ABC of a vector R is equals, if a vector is given in your component form as x I hat plus y j hat plus z k hat are the just respective components. That's it. A will be x, B will be y, C will be z. That's it. So your comparing this form, you can directly say that direction ratios will be A is equals to 1, B is equals to 1, C is equals to minus 2. And in order to find your direction cosine, which are L, M and N, this means 1 A is equals to, okay, sorry, 1 is equals to, clear, 1 is equals to A by magnitude of R. Okay, so magnitude of this will be root 6. As you can see, 1, 1, 4 and then root, you will have 1 by root 6. M will be, so this is your L. Okay, this is your M. M will be B by root 6. B is 1, so 1 by root 6. N will be C by magnitude of R. This means minus 2 by root 6. Okay, clear? So thus your direction cosines will be 1 by root 6, 1 by root 6 minus 2 by root 6. So this is it for now. We will be back as time is running out. So we have to stop here. So this is it for now. We will be back with more concepts and more examples to get this chapter, vector algebra. So again, thank you all.